let us draw some conformers of butane and see what the stability order is for them. Alright, so let's check out. So I have butane and I am drawing conformers for butane. So I have taken C2 and C3, the second carbon and the third carbon. So I have taken the second carbon out here. This is second carbon, so it has 3 bonds. So I have taken one methyl, then hydrogen, hydrogen. See where I am drawing, I will just explain it to you. So I am drawing for this is second carbon, 1, 2, 3, 3 and 4. Alright. So I am drawing conformers against second and third. Alright, for second and third. So this is second carbon. Alright. Now I am taking the third carbon. This is third carbon. So second carbon, you can see 2 hydrogens are there and 1 methyl is there. And at the third carbon, this is third carbon. So this will have 2 hydrogens over here and 1 methyl group. So I have taken 1 methyl and there are 2 hydrogens. So I have taken this conformer for butane and you can see all are overlapping. So this is eclipse form, this is eclipse form. Now if I rotate any carbon, if you can hold on second carbon and you just rotate third carbon by 60 degrees, what do you get? You get something like this. I have kept second carbon as such. So second carbon is this. These are the bonds at the second carbon. I am rotating the third carbon by 60 degree. So the groups become like this. Alright. Now I have rotated by 60 degree. Here the theta angle was 0 degree. Here theta is 60 degree. Now again if I rotate it by another 60 degree, what do you get? You get something like this. Here methyl is there. I am not rotating the second carbon, I am rotating the third. Now you will have methyl here, you will have hydrogen over here, you will have hydrogen over here. Alright, by 60 degree we have rotated. If I rotate by another 60 degree, what I'll get? Check out. By 60 degree if I am rotating the third carbon, I'll get something like this. See, second carbon I have kept constant, I am just rotating the third carbon. So now methyl will rotate and it will come here and the hydrogens will go here. Now the degree of angle rotated overall is 180 degrees, right? So this form is called eclipse, this is called gauche. This is called gauche form and this is called partially eclipsed. This is called partially eclipsed. And the last one is staggered, or we can call this as anti. You can call this as anti. As you can check out, all the groups are far apart, so they are arranged beautifully, so they are stable. So and stability and energy are inversely related. If I have to say which will be the lowest in energy, so staggered is most stable and lowest in energy, and which is least stable, see highest repulsions, because all groups are overlapping completely. So there is least stable and highest energy. Stability and energy are inversely related. Least stable, high energy; most stable, least energy, right? Energy stability inversely related. So what is the order of stability? Most stable is anti, most stable is anti, then gauche, then partially eclipsed, and eclipse is least stable, and energy is in opposite order. So we have a graph out here where you can check out this eclipsed, highest in energy, and you have anti, which is in lowest energy. You have at y axis energy is there, so highest energy is for eclipse and lowest energy is for anti. So energy and stability are inverse in relation. Stability order we have already discussed: anti, gauche, partially eclipsed, and least is for eclipse. Energy, you just flip the order. Sometimes gauche becomes more stable than staggered. What are those cases? Those cases are where hydrogen bonding is there between groups. Such as one such example is ethylene glycol, where OH and OH groups are present and they have intramolecular hydrogen bonding. So in ethylene glycol, gauche becomes more stable than anti or staggered. So gauche is more stable than anti when there is presence of intramolecular hydrogen bonding. Otherwise staggered or anti is more stable than gauche. Thank you so much.